Welcome to the deep dive. If you've been writing code over the last few years, you know the power of AI assistance. But for a long time, these tools were essentially a very smart sidecar.
Right, they'd suggest the next function or maybe autocomplete a comment. They were passive.
Totally passive.
They functioned in what we call the sidecar paradigm. The AI gave you text suggestions, but the heavy lifting of figuring out, where to put that code, how it integrates with the actual file system,
And whether it even worked.
and whether it passes the test, yeah, that was still all on the developer.
But our sources today confirm we are seeing just a fundamental shift. We are diving deep into Anysphere's composer model, which is really leading the charge toward what the industry is calling agentic coding.
And that's the critical difference.
This AI doesn't just offer advice, it takes ownership.
It takes ownership of the task.
Yeah.
When we talk about agentic coding, we mean the AI is capable of executing these complex multi-step tasks. It, traverses file trees, executes terminal commands like grep, and applies multi-file diffs to update your whole project. It acts like an independent agent.
And that is our mission today. To technically deconstruct Composer, we need to understand the architectural choices, the training methods, and the hardware optimizations that let them achieve this. Because a major finding in our sources is that the really big general-purpose models—
Your GPT-4os, your Gemini 1.5 Pros.
Exactly. While they are amazing reasoners, they often lack the critical latency profile required for a developer to actually stay in a flow state.
That's the key.
Okay, let's unpack this, because that concept of latency as a non-negotiable requirement, it seems to be the core philosophy driving everything Anysphere built.
It really is. If you look at their founding ethos, they weren't interested in just, wrapping an existing API. They saw the company as an applied research laboratory.
Okay.
And their focus was on solving these deep friction points in modern software integration. They realized the friction wasn't just generating code, it was the painful process of putting that code into a huge existing code base.
Which led them to take total vertical control, right? They didn't just build a model, they forked VS Code to create Cursor, which gave them the environment.
The body, yeah.
And then they realized they had to control the brain, too.
Absolutely. Relying on external APIs meant unpredictable delays. That makes true agentic behavior pretty much impossible. And that realization drove this pivotal internal prototype they called Cheetah.
Ah, the famous cheetah experiment.
Yeah.
I remember the rumors floating around that because it was so fast, it had to be a fine-tune of something like xAI's Grok.
Right, but our sources debunk that entirely. It was developed in-house to test one sort of radical hypothesis.
Which was?
The hypothesis was simple but profound, that latency is a functional component of intelligence when you're talking about interactive coding.
A functional component of intelligence?
Yeah, think about the math. In an interactive loop, a developer would vastly prefer a model that is, say, 90% correct in 500 milliseconds
Okay.
over one that's 99% correct but takes 10 seconds to respond.
Wait, so they're trading absolute theoretical perfection for flow state.
Exactly.
That's a completely different product strategy. The faster feedback loop lets the human correct the small error and still finish the whole task faster.
Precisely. It transformed the user experience. You move from that frustrating request and wait model to a fluid, real-time collaboration. Composer was basically built as the smarter, scaled-up version of Cheetah.
So it kept the extreme speed but boosted the reasoning.
Yep, using advanced techniques like mixture of experts and reinforcement learning, aiming for a consistent target of about 250 tokens per second in production.
So the burning question is, how do you get that reasoning capability while hitting Cheetah-class speeds? You can't just scale up a standard dense model, right? The cost would be insane.
You can't. And this is where it gets really interesting. Composer uses a mixture of experts, or MOE architecture.
MOE. Okay, let's break that down.
The MOE architecture is the secret weapon for decoupling knowledge from cost. Think of the model not as one giant brain, but as like a specialized tech team. The total parameter count, the stored knowledge, is massive, hundreds of billions.
Like having thousands of specialized engineers on staff.
Exactly. But for any given task, you don't need your database expert to weigh in when you're debugging a React component.
Right.
The MOE architecture routes the input only to the relevant specialist experts. A small subset, maybe just 10 or 20 billion parameters that are active for that query. This just drastically cuts the computational cost.
Encoding is so modular, it seems like a perfect fit for MOE, doesn't it? You're jumping from Python to YAML to C++.
It leverages the inherent sparsity of code. One set of experts can specialize entirely in, say, system configuration files. another in low-level memory programming. It saves compute while maintaining this really broad knowledge
Just
base.
250 tokens per second. That's
Yeah.
more than just a smart architecture. Where does that raw throughput really come from?
This brings us to the low-precision training detail, specifically the MXFP8 breakthrough.
Okay, yeah, this is a deep cut into ML systems engineering. Historically, large models train in 16-bit precision. Great for stability.
But to run inference cheaply, you often have to quantize or shrink those weights to 8-bit. And this shrinking process introduces what's called the quantization gap.
A performance-degrading instability.
Exactly. So you train this high-quality thing, but when you shrink it for production, you take a hit.
So how did Anysphere get around that?
They avoid it entirely. They train natively in MXFP8. By applying some advanced dynamic scaling methods, that's the microscaling part, they maintain stability while training the model in the exact same format it will run in production.
So the production model it's mathematically identical to the training model.
Yes, and that's the critical enabler for speed. This approach lets the inference engine completely saturate the transformer engine on NVIDIA H100 clusters, hitting that 250 TPS goal without the efficiency penalty.
Okay, let's indulge in a little community detective work. Anysphere has been pretty quiet about its base model, but what are the forensics telling us?
The community has been busy with tokenizer forensics, and the evidence, specifically the large 128K vocabulary size and the really efficient tokenization, it strongly suggests a foundation related to a big open source model.
Like Llama 3.
Like Llama 3, or maybe more likely given the MOE encoding focus, an architecture descended from DeepSeek.
Ah.
DeepSeek really pioneered these efficient MOE coding models, and it seems almost certain Anysphere adapted or heavily fine-tuned one of those high-performance open architectures as their starting point.
So we have the MOE architecture as the efficient fast access brain.
Right, but to get the skill, the agency, to actually use tools and navigate a real code base, you need more than just static data. And this is where reinforcement learning, or RL, steps in.
Why is RL so necessary here? Doesn't training on all of GitHub teach it how to write code?
It teaches it to predict code as it appears in a final commit. The clean, polished result.
Finished product.
The finished product.
Yep.
It never sees the actual messy process. The stack traces, the broken tests, the debugging loop where code fails 5 times before it works.
I see. So a statically trained model, when asked to fix a bug, it's just guessing based on patterns. It hallucinates file paths?
It tends to, yeah. Composer instead is trained for interactive agentic behavior. They treat the entire IDE environment as a giant game.
And what kind of behaviors are they rewarding in that game?
The reward functions are really sophisticated. They incentivize what they call tool efficacy. The model is rewarded for using grep or file system commands to verify a file path instead of guessing it.
That's a huge deal. That's probably the biggest suppressor of file path hallucination.
It is. And they also reward parallelism. Because, users are impatient, the model gets a better score for issuing 3 file read requests in one parallel turn rather than 3 sequential ones. It learns to optimize for wall clock time.
This sounds like a monster of a systems engineering task. I mean, unlike chess, where a training game takes milliseconds, a coding task, you have to spin up an environment, install dependencies, compile. That could take minutes.
And you've just perfectly framed the straggler problem.
What happens when your multi-million-dollar H100 cluster has to wait for a slow compile step?
Right, your whole training pipeline grinds to a halt.
Yeah.
Anysphere solved this with a custom orchestration layer built on Ray. They use a massive fleet of concurrent microVMs, these lightweight virtual machines, to execute the agent's commands asynchronously.
So the experience generation, the actual coding and compiling, is completely decoupled from the training loop.
Exactly. The GPUs never sit idle. They're just constantly ingesting this stream of asynchronous data from the microVMs.
And the sources highlight a key competitive advantage here.
Yeah, they use the exact same infrastructure for training that they use for their production Cloud Agents product. This means there's zero sim-to-real gap. The model is fine-tuned for the very environment the customer is paying for.
Okay, so we have the fast MOE brain and the RL-tuned agentic skill. Let's talk about the user experience. That 250 TPS speed is often radically enhanced by a technique they call fast apply.
Or speculative edits, yeah. It bypasses the standard autoregressive bottleneck. If you ask a normal LLM to change one line in a 500-line function, it has to regenerate all 500 lines, token by token.
Which takes forever.
It does. Composer realizes that most of the code is unchanged. It uses a deterministic algorithm to rapidly speculate that huge chunks of code are identical to the original file.
And then the powerful MOE model just verifies those chunks in parallel. It's verifying, not generating.
That is the crucial distinction. That verification step lets Composer skip the unchanged blocks. And for small surgical changes, it gets a reported, 13x speed up over traditional inference?
13 times.
That's not rewriting the file at 250 TPS. It's confirming that 99% of it doesn't need to be rewritten. The effective speed feels like thousands of tokens per second.
Of course, for any of this to work across files, you need context. You can't just stuff the whole code base into a context window. So that brings us to retrieval augmented generation, or RAG.
Right. And for code, RAG is even more vital than for simple text. Composer uses a multi-stage system: query generation, retrieval, and then a really crucial re-ranking step.
What does that do?
It's not just retrieving related lines of text, it's retrieving specific structural information, a function signature from an imported module, a class definition. The re-ranking prioritizes that structured code context, so only the most critical information actually fills the model's context window.
All the speed has led to a cultural shift people are calling vibe coding.
Vibe coding, yeah.
The developer's job shifts from writing syntax to reviewing behavior. You're operating at a higher level, almost like a project manager for the AI.
It's massively efficient, but this fast pace does introduce risk. The sources point out that the accept-all mentality that gives you the speed also bypasses the friction, the reading, the thinking that was historically a quality gate.
So you risk accumulating these confident hallucinations.
Or subtle security vulnerabilities that a developer moving too quickly might just miss.
Let's touch on the economics. They're offering this for a flat rate, $20 a month. How is that even sustainable when a dense frontier model can cost tens of dollars per million tokens?
It's all about the optimization. The MOE architecture and the MX FP8 training, they just drastically reduce the cost per token. And this aggressive pricing isn't just about profit.
It's strategic.
It's very strategic. The low flat rate is designed to capture market share and, most importantly, build the RL data flywheel.
Ah, that constant stream of human acceptance and rejection data.
Exactly. That's what they need to train Composer 2.0 and beyond.
So if we synthesize all this, the central finding is pretty clear.
Yeah, Composer isn't just a slightly better model. It is a triumph of systems engineering and vertical integration. The value is in co-designing the model, the training stack, the inference engine, and the UI all together.
So the big takeaway is that the real competitive advantage in the AI era, it isn't just the core model weights, which are becoming commoditized. It's the speed and the integration.
Has to be.
Composer's defense against rivals like Copilot and even the open weights models like DeepSeek is its highly RL-tuned expertise in using the specific tools of the Cursor IDE at lightning speed.
That's their mode.
So here's a final provocative thought for you to consider. Composer shows that true agentic intelligence, because of the MOE memory requirements and the RL infrastructure, it increasingly requires these massive cloud clusters. What are the implications if this leads to, I don't know, the end of the local host? Where your local code editor is no longer the center of gravity, but merely a thin, fast client for a powerful cloud agent's output?